Welcome to AP Chapter 6, Thermochemistry. Potential energy, while it's often used in physics, it is used in chemistry. But first, to get an idea of what potential energy is, let's start with potential energy in terms of a physics definition. And potential energy is defined as the mass of an object, the gravity that is affected to the object, I guess is a better way to say it, and the height of the object. Now, both the ball and the bow have stored energy, the energy of position. Now, gravity and distance. So if I held a solid lead box high above your head and let it go, okay, yeah, I know that would be really sadistic. But anyway, the distance would be so large that the potential energy is extremely large, and thus, when it's converted to kinetic energy, can do significant damage to your head. But if I dropped it onto a table, the distance isn't as high, so the gravity factor, well, it's pretty consistent, but then the potential energy is not as great because your distance is not as great. Potential energy and the distance are directly proportional. This ball possesses a ton of potential energy just by its position at the top of the hill. Now, if the ball were to start to roll, its potential energy would be converted to kinetic energy. If ball A were let go, the potential energy would be converted to, yeah, you're right, kinetic energy. But ball A, held in place, has energy of position simply by the fact that it has the potential to do some damage on B. Chemistry is where we really look at potential energy. If the reactants have more energy than the products, then we say that this is an exothermic reaction. Notice if I were to draw a line between reactants and products, it would be a downhill slope. Potential energy is all about the initial position. Taking a look at this particular graph, it shows reactants going towards products, potential energy on the y-axis. Reaction pathway, at this time in our education, we can think of it as the time over which the reaction proceeds. As you notice, for the reactants to get to products, the slope is uphill. That means we have to put energy into the reactants to drive them towards products. This would be called an endothermic reaction. You have to put energy into the reaction to make it happen. In this graph, notice that the potential energy of the reactants is greater than that of the products. So if we were to draw a line from reactants to products, the line goes downhill. This means the reaction releases energy to get to products. This is an exothermic reaction. Now we're ready to actually talk about the first law of thermodynamics. Yay! In an absolute perfect world, the first law of thermodynamics states that the energy in a chemical reaction is neither created or destroyed, only changed. And in fact, this could be even more than just a chemical reaction, just a physical change. Energy is neither created or destroyed, only changed. Let's take a look at this definition called work. And no, I don't mean go to work. I mean actual work. It's a physics definition, work. And I guess you could call it a chemistry definition if we had to, but physicists like to claim this as their own. Well, in order for work to be done, you need a force executed through a distance. So take a look at this first example. You got a person pushing a box. You've got a direction of force. You got a direction of motion. Is this work? Yes, it is, because you have a force being pushed through a distance. Take a look at this. You have a person who is holding up a book bag. So the direction of force is straight up, but her direction of motion is sideways. So would this be classified as work? Nope. The force and the direction of motion need to be the same. Take a look at this picture. She's picking groceries up? Yes, you're right. This is work. Last example. Holding the bag up, but walking. Feels like work, but according to physicists, no, it's not work. The direction of force and the direction of motion have to be the same. We're going to use this first law of thermodynamics for just a little bit, just using this basic equation. I'm not sure why delta U is often used. I prefer to think of it as delta E for the change in internal energy. The hardest part of this is the signs. And heat, of course, we use the letter Q to represent heat because that is the quantity of heat added to a system. The negative W represents the work done by the system. And those to and by words actually have a lot of meaning. So let's take a look at another slide that hopefully makes that more clear. Now don't freak out about the fact that this equation at the top is different than the one on the previous side. I will explain how the signs work in just a moment. But if you recall, whenever we talk about endothermic reactions, you have to define both the system and the surroundings. And everything is always from the point of view of the system. Within this equation, Q, of course, refers to the quantity of heat. And if heat is going into the system, that is an endothermic reaction, and Q will be positive. If heat is exiting the system, then Q will be negative for an exothermic reaction. W sign also changes. When the surroundings does work on the system, that causes the internal energy of the system to go up, and W then will be positive. When the system does work on the surroundings, that causes the internal energy of the system to go down, and then your work value is negative. The biggest part of these problems is trying to figure out the sign on Q and the sign on W. For instance, in this particular problem, we have an endothermic process. So the sign for an endothermic process is positive. Now, where work is done on the system. Now, if work is done on the system, that means the internal energy of the system goes up, and then W is positive. Adding those together with the correct number of sig figs, we get 17 joules. Working on this problem, looking at the formula, we have to determine the signs again of both Q and W. If it absorbs 45 kilojoules of heat, that means it's endothermic and the value of Q is positive. Now, if it's doing work, that means the internal energy must go down, making the value of W negative. Paying attention to significant figures, we end up with 16 joules. If you're releasing heat energy, you're exothermic, so the value of Q will be negative. And if work is done on the system, that means the internal energy is increasing and the value of W will be positive. So your final answer then, paying attention to sig figs, is negative 21 joules. Those homework problems are very similar to the problems I just went through.